Hello, my name is Gregor Hollis and I'm responsible for the topic data replay at dSPACE. In this presentation, I will focus on the data replay toolchain and how it can help reducing cost and accelerating the development process of autonomous driving. To sufficiently test all parts of the processing chain, the validation strategy for autonomous vehicles comprises a mix of test methods. Each of them has its strengths and weaknesses. Data replay, also called data reprocessing, is an open-loop test based on injection of sensor data recorded during real test drives. Thanks to the highest realism which can be achieved in the lab, data replay is an integral part of each test strategy for validation and homologation of perception-driven ADAS and automatic driving functions. In contrast, closed-loop testing is the most common method and offers the biggest test coverage. It is the first choice when it comes to the validation of driving and control functions. Despite limited realism of simulation models, closed-loop testing with synthetic sensor data can be a good addition to data replay for testing perception in case of re-recordings are missed or rare, like for corner use cases and dangerous situations. Today, proving ground and real-road testing are essential for vehicle homologation. However, due to complexity of Level 3+ vehicles and shorter software update cycles, more frequent component and vehicle type approval will be required soon. This will not be feasible without making homologation digital by further increase the share of lab-based verification and validation in the vehicle approval process. The ASAM Test Specification Study Group compiled and published a report that reviews relevant test methods and use cases for testing and homologation of the ADAS AD in the automotive industry. According to that, data replay is seen as a key part of consistent and qualified V2V pipeline with focus on interface testing, safety, verification including hardware, and system performance. Many customers struggle with significantly higher costs of data replay compared to classical closed-loop testing. Data storage and annotation, test systems, and the infrastructure required for deployment and operation are often considered as key cost drivers. A closer look at the major steps of the process can help to identify cost-saving potentials and recognize advantages that a consistent toolchain for data replay can offer. We will start the journey with data collection. We will learn about the role of indexing and sensor data management to gain data insight, and we will get some insight into flexible and scalable data replay and test management that helps accelerating validation of ADAS AD. Finally, when some time is left, we can have a quick look at the smooth transition from replay to closed-loop testing and how the same data and the same system can be used for both. A big volume of data must be collected to validate perception functions for cars of autonomy level 3 and higher. A vehicle equipped with 12 cameras, 8 LiDAR, and some further radar sensors can generate about 18 terabyte data per hour. One effective measure to save costly storage is to use compression algorithm while logging. The Altera logging station can be equipped with a high-end GPU to perform H.264 video encoding in real time during the recording. Benchmarks show that up to 27 camera streams can be encoded in parallel, and more than 50% of storage space in original quality can be saved when using lossless compression. This means up to 72 terabyte less data per hour needs to be transported to data center. With lossy compression at highest quality level, the required storage space can be further reduced to up to 2% of the original size. However, just compressing data is not worth much without providing proper descriptions and having a chance to search data for specific content afterwards. This data enrichment process is called indexing. and it begins already during real test drive. Using a tablet or PC remotely connected to Altera logging station, a set of predefined and custom labels can be used to manually tag the recording. It could be annotations about specific driving conditions, events, traffic signs, and more. This process can be even automated to some extent when Altera is additionally equipped with a GPU. In this case, smart tagging component can be installed and executed in parallel to the recording. During smart tagging, a deep neural network algorithm performs object detections of cars, trucks, bicycles, and pedestrians and automatically labels recordings on the fly. The recorded and initially labeled data is usually brought into on-prem or colocation data center, where a sensor data management software like IVS comes into play. IVS can be used to perform all required tasks like a further detailed and fine-tuned data indexing to get a fully searchable database that helps separating the wheat from the chaff. Later, during preparation for data replay tests, IVS supports efficient search for relevant situation against petabytes of recordings saved in different locations. IVS utilizes taxonomy trees to perform data indexing in a systematic way. Taxonomy is a hierarchical classification where tags are organized into groups or types so that search queries can be created and processed more intuitive, and content, in this case specific recording or part of them, can be found easier and faster. IVS supports import of user-defined taxonomies, for example to add specific ODD, operational design domain, that describes conditions under which a given driving automation system is designed to function. IVS data management offers a number of indexing jobs that can efficiently be applied on large data volumes. One job example is the AI-empowered automated maneuver recognition based on camera data. A deep neural network can detect cut-in, cut-out, or lane change maneuvers and stick the related tags with correct timestamps to recordings. In cooperation with our partner X-Ways, also indexing based on object detection for LiDAR point clouds is available. Thanks to SLAM and 3D environment reconstruction, the LiDAR annotation pack performs tagging of objects like buildings, trees, or streetscapes together with their relative positions. Further indexing jobs examples are the digital map or participants annotator. The map annotator extracts information out of different map formats and by combining it with GNSS traces generates tag entries for speed limits, traffic signs, number of lanes, or road elements like intersections. The traffic participants annotator is able to recognize and tag vehicle classes, pedestrians, or animals. This is a concrete example that shows how easy a search query can be created via the web front end of IVS. Thanks to the taxonomy tree, the user is guided through available tag groups and entries, and he is free to combine them in different ways to intuitive requests like search for vehicles on roundabout at daylight. After sending a query, IVS looks in all recordings for tag entries that fit these specific tag combinations and lists the results in form of scene previews. Now, interesting scenes can be individually selected and combined to datasets for replay test. As presented, indexing data is an essential step to make recordings searchable and thanks to that usable. Based on indexing, customer can gain data insight and create effective filter to reduce a huge number of recordings to significantly smaller but highly valuable content. Data selection by filtering is essential since the subsequent steps like data annotation and storage in the public cloud are much more expensive than data logging. In practice, up to 90% of recordings is redundant and will not pass the filter. This data can be archived in data centers or even deleted. On the other hand, data insight and systematic filtering also help to figure out data gaps and underrepresented data groups. Those white spots can be later closed by additional logging campaigns or to some extent by adding scenes based on synthetic sensor data of high quality. To reduce storage and computation costs, IVS data management also supports hybrid cloud approach. After transporting and saving data in a data center, dedicated IVS jobs can be applied on the recorded data to generate previews out of it and to upload them to the public cloud. The previous data is massively reduced to just 3% of the initial data volume. The original recordings are still linked to the related previews, which allows IVS to use the previews as alias for searching content and performing computation-intensive jobs like format conversion, anonymization, and pre-annotation directly from the cloud on the original data located in a data center. After learning some methods for more efficient data collection and selection, let us have a quick look on some essential aspects when looking for cost-effective data replay systems. Perception can be implemented on multiple levels of complexity. The more a tool provider learns about the SUT in the bidding phase, the better his offering can be with regards to performance and price. For low-level SUTs, the perception unit is usually integrated with the sensor component. In this case, a smart sensor such as camera, radar, or LiDAR is responsible for object detection and interpretation. The result is provided as object lists on sensor output and connected to the vehicle bus. Requirements for replay systems to test smart sensors are quite low due to low number of interfaces and reduced bandwidth. In contrast, a sensor fusion unit is a more advanced SUT job. It combines at least two sensors, typically a camera that streams video via a specific raw data interface and a smart radar that provides object lists. The fusion algorithm compares those different sources and merges data to a single object list on output. To enable sensor fusion working properly, input stream must be perfectly time correlated. Accurate time synchronization and low jitter are essential requirements to consider when looking for data replay solution for sensor fusion. Finally, at the right-hand side, you see the HPC, the high-performance computer. For example, a domain controller of self-driving car. It is the most complex SUT type with highest integration level. A single HPC can comprise different software components like perception, data fusion, or even driving functions, including prediction, motion planning, or motion control. HPC can be connected to a variety of sensors via raw data link or vehicle buses and requires a reprocessing system being capable to provide a high number of heterogeneous interfaces and to establish high data throughput connections. To cover a wide range of SUTs and complexity levels and to easily integrate with existing tooling, a test solution for data replay should follow a modular approach. Key advantages of the validation system provided by dSPACE are the replay accuracy, correctness, and flexibility. During reprocessing, the recorded data, which can be saved in different formats like MDF4, PCAP, or ROSBAC, is streamed out to sensor interfaces by the replay software RTMaps running on PC. RTMaps has been designed to deal with asynchronous data streams and supports timestamping. Thanks to that, it is capable to replay in exact time-correlated manner. The replay server offers enough performance for doing additional pre-processing jobs like insertion of dirt or pixel errors prior to the actual data injection. After leaving the replay PC, data keeps time correlated thanks to PTP-based hardware synchronization between the bus and raw data injection units. The bus injection hardware feeds the data with minimum jitter via CAN, Ethernet, FlexRay or LIN, and the performance can be exactly tailored to customer needs. Depending on required replay protocols like UDP or SOM-IP and the bus security level, different Scalexio real-time hardware can be used. Raw sensor data connection is established via CSI2, FPD, Link or GMSL. Depending on SUT requirements regarding data throughput or number of connected sensors, a more compact or more flexible raw data injection hardware comes into play. I will explain that in more detail on the next slide. In parallel to raw and bus data injection, measurements are taken on the SUT output and passed to the KPI calculation component to be compared with related ground-truth information which was created during data annotation. Key performance indicators allow making assumptions about the maturity level of the examined SUT. The calculation is often implemented by customers. I will show some examples for KPIs later. The most components of a data replay system can be reused for closed-loop here simulation. That makes the solution even more attractive with respect to the return of investment. As mentioned, depending on the use case, different hardware devices can be used to feed raw sensor data to a SUT. The environment sensor interface unit on the left offers the highest flexibility. Thanks to the high-performance FPGA, the device can be connected to up to 16 camera sensors with an aggregated data throughput of up to 35 gigabits. This makes the ESI unit to a perfect solution for connecting data fusion and HPC-based SUTs. In contrast, the sensor data interface unit is more compact and can be offered to lower price. With up to 20 gigabit per second data throughput, the FPGA-based SDI unit can feed data into 1 or 2 cameras in parallel and is recommended for smart sensor or sensor fusion testing. One further important aspect to consider is the fact that a replay system has to deal with changes. Since logging and enrichment of data is expensive, a key objective is to reuse once recorded data as long as possible for next generation of SUTs. The way how SUTs evolve can vary. Algorithms can change, sensor driver might be uploaded, communication within vehicle bus and timing can be different compared to the time of the recording. This slide briefly shows it on an example of bus security. Secured bus data frames will only be accepted by the SUT when a MAC verification can successfully be performed. Since the ECU internal security keys regularly change, the dSPACE replay system needs to adopt those changes to the existing recordings. For this purpose, an additional algorithm runs on Scalexio in real time, which does some pre-processing. It opens the relevant part of each bus data frame to be replayed, updates the security-related values according to the needs, and recalculates the MAC of the frame. The manipulated frames are passed to the SUT. A quick jump to the KPI topic before continuing with software data replay. To calculate KPIs for detection algorithms, a classification of detections needs to be considered. The so-called true positives stand for correct detections, like a traffic sign on right-hand side in this picture. In contrast, false positives describe wrong detections, like the white car on the left side, which must not be taken into account since it is leaving the roundabout before the ego vehicle enters it. Situation-relevant objects not detected by the algorithm, like some traffic signs in this example, are classified as false negatives. Concrete examples for perception-related KPIs are the accuracy metrics like precision, recall, and F1, which set the detections classes described before in relation. A further KPI used for object detection algorithm is the bounding box accuracy metric, also called intersection over union. Intersection over union describes the overlap between detections and ground-truth bounding boxes for each detected object. The higher the value of an accuracy metric is, the better is the quality of the object detection algorithm. In best case, each value should be equal to 1. Even if testing of real hardware is an essential part of validation, since it makes sure that timing, constraints, and specific hardware platform behavior can be considered properly, we expect that majority of tests will be done on software level in the future. To support this, the dSPACE software data replay solution allows testing of perception algorithms and subsequent AD layers on functional level. That comprises generation of virtual SUTs out of code developed in Python, C, C++, standalone, or embedded in AutoSAR or RTMaps middleware. SUT generation and replay testing can be easily integrated into customers' CI/CD pipeline. The way how a virtual SUT is connected to the software replay system and the architecture of the setups looks very similar to hardware reprocessing. Same data recordings can be played with RTMaps. However, the interfaces that feed raw and bus sensor data into a virtual SUT are now software-based. To achieve high sensor data stream performance, a zero-copy approach is used. Raw data injected by the VESI component is kept in shared memory and directly accessible by the SUT. Thanks to capabilities of the offline simulator VEOS, software reprocessing can be performed faster than real-time on x86 platforms, or done in co-simulation with an ARM architecture as processor and a loop-based replay. Each component is Dockerizable and can be orchestrated via Kubernetes. That makes the solution scalable and ready for massive parallelization in the cloud using dSPACE Synfera test management and orchestration platform. Which leads me to the next slide. So far, we learned how proper sensor data management can contribute to significantly reduce the overall data volume to the relevant and valuable content. I also gave a quick overview of dSPACE flexible solutions for hardware and software data replay that can perfectly be matched with all relevant types of SUTs and reduce development time and costs. Now, I would like to add the last puzzle piece to the data replay toolchain, which is Synfera Data Management Platform. This slide shows the whole workflow for data replay testing. From each corner of the globe with available internet connection, a test manager can access IVS and Synfera via the web front end. First of all, he needs to find suitable recordings for his tests by using queries in IVS. Based on those queries, IVS lists all preview recordings that match the criteria to help select the right scenes and combine them to datasets. Once the required datasets are selected, Test Manager can start creating test suites in Synfera. For each data replay test, at least one dataset, a target replay station, and related SUT must be specified. The replay system can be software or hardware-based and located in a public cloud or data center. During test execution, each dataset is downloaded to the related test station and processed as replay job, sequential or in parallel to other jobs orchestrated by Zinfera. KPI calculation can be done on the fly or in post-processing, and the reports are finally accessible via Zinfera web front-end for evaluation. After introducing the whole data replay testing workflow, a final picture of the toolchain can be drawn. The decision where to deploy the single part of the toolchain can have a big impact on the total cost of ownership. Generally, dSPACE follows the technology-agnostic approach, so the customer is free to deploy single parts of the toolchain wherever he wants to. Practically, several aspects like public access, scalability of test results, or data storage and infrastructure costs must be considered. For the best accessibility, data and test management are often located in the public cloud. For data storage and replay system, this can vary. For example, a startup company which focuses on development of perception algorithms will initially not invest much in own test infrastructure. They will probably keep their data and validate the algorithms by using software data replay in the cloud without fearing high data egress costs. For classical OEMs and system integrators or T1s who deal with real SUTs, this might be different. They usually collect a lot of data and have their on-prem test facilities today. We see some of those customers tend to bring their hardware data replay systems into colocation centers, where they can profit from the existing infrastructure and good connection to the public cloud. dSPACE works with partners on joint solutions that help customers to combine the flexibility of public cloud with advantages of on-prem deployment and to save costs. This slide is just an example how a hybrid cloud solution for hardware data replay could look like. Data and test management tools, as well as annotated data recordings and test results intended to be used globally, are located in the lake of public cloud. This way, datasets can be added and selected, tests planned and executed, and results evaluated from everywhere. The actual compute infrastructure, including dSPACE replay stations, is deployed in a data center. Thanks to local storage, volumes of recordings can be pre-processed locally and the data traffic between data center and cloud storage reduced to save costs and public cloud egress. Hybrid cloud approach has potential to become a successful deployment model, not just for data replay, but also for closed-loop testing. Finally, I would like to briefly introduce the dSPACE service called Scenario Generation from Measurement Data and Sensor Realistic Simulation, which serve as a bridge between data replay and closed-loop testing. As mentioned at the beginning, corner cases or dangerous situations are quite rare. A chance for getting them recorded during real test drive is quite low. In this case, a service offered by dSPACE and our partner Understand AI can help. SCGM can reuse data initially recorded for replay testing. A deep learning-based service provided by UAI gets front camera recordings and related GNSS trace files as input and generates scenario descriptions file out of it, with road topography, traffic participants, and their movements. The description file is in the next step imported by dSPACE tooling to generate simulation model of road network, 3D model of surroundings, and logical scenarios with maneuver descriptions for ego vehicle and other road participants. generated model artifacts match to high extent with original real recordings. This digital twin can now be modified and executed in open or closed-loop simulation, including generation of sensor realistic camera data. Let us imagine that a real-world recording is available where an ego vehicle approaches a roundabout and meets a fellow car that is already using it in a proper way. After SCGM has generated a simulation scenario out of this recording, maneuver definition of the fellow vehicle can be modified to let the car drive in a wrong direction. This modified scenario can be utilized for closed-loop sensor realistic simulation to test the behavior of the SUT in a critical situation. Even though large-scale testing and homologation of perception functions is not feasible when using synthetic data, sensor realistic simulation can be a reasonable approach to close the gap where real data is missed. However, the quality of synthetic sensor data needs to be as close as possible to the real world. With Aurelion, dSPACE provides a collection of physics-based sensor models which are executed on PC with GPU acceleration to generate realistic raw sensor data for camera, radar or LiDAR. To point out a few highlights, SRS provides high-fidelity camera streams that consider realistic lens profiles and lighting effects and allow picture modifications, like for example distortion. The radar model supports multipath propagation and is able to interact with targets, and the LiDAR model supports scanning and flashing sensor and is reactive to weather conditions. Since the sensor data generation is based on road and environment simulation, the ground truth reference data is available by default. This slide shows a closed-loop hill setup that can simulate rare use cases for testing perception. As mentioned before, most components utilized for data replay can be reused here. We see the same hardware for injection of raw sensors and vehicle bus data. Key modifications are highlighted in red. The SUT output is now linked to the Scalexio to close the loop. In the setup, Scalexio additionally acts as a real-time simulation platform. The simulation output, which is continuously generated out of vehicle dynamics, traffic and sensor models by ASM on Scalexio, is fed to Aurelion sensor realistic simulation to generate synthetic raw sensor data and to inject them into SUT via ESI or STI unit. In general, the additional investment to cover data replay and closed-loop testing in one setup can mainly be reduced to simulation software and one or more sensor simulation PCs with powerful GPU for running physics-based sensor models. In this presentation, I briefly introduced the dSPACE toolchain for data replay testing. I presented features like compression, labeling, and indexing that allows to significantly reduce volume of recording and lower data storage costs. Due to high flexibility, dSPACE test solutions can be connected to all relevant types of SUTs and perform data replay with high accuracy that helps to improve test quality and to reduce development time. Due to modular and technology-agnostic approach, each part of the validation toolchain can be easily integrated into existing test infrastructure and deployed on public cloud, co-location, or on-premise data center. Reuse of components allows seamless and cost-optimized shift from data replay to closed-loop testing. Thank you for listening, and I'm looking forward to your questions.